Okay, we're going to start off with shine like a star, using the STAR method in behavioral interviews. Before I go into STAR, the first part of this is, what is a behavioral question, also known as a soft skills question? It's a question you're going to get as part of your technical interviews. It's either going to be a question at the end of a regular technical interview, so please code this problem. By the way, tell me about how you're a leader. Or it's going to be a separate interview where it's just a series of behavioral questions. And so the company wants to know what type of leader you are, especially if you're in senior positions or management positions, how you collaborate with your team, and your ability to deliver. This doesn't necessarily mean that every behavioral question you have to say, I deliver everything on time perfectly. It just means, do your values align with the company values? For example, deliver fast versus deliver with quality. So there's really no right or wrong answer to these in some cases. You just want to make sure you display whatever traits the company is looking for. And you can find out which traits the company is looking for by going to their careers page. And they often have a list of company values. So that's a good way to prep for these questions, is go to the company's career page, look at the company values, and try to prepare examples of how you display each one. Going to the STAR method, this is the sort of top recommended method for answering these questions. And it's also the method interviewers are trained in. So interviewers are looking for this. And so practicing this can be really helpful. STAR means situation, task, action, result. So I will go into that in the next slide. So we start off with situation. You describe what your role is, where you're working, what type of team you were working on, how many people, were you a manager, were you working at a small company, a big company, were you working on a website or data science pipeline, that kind of thing. Now I'm going to call out here that if it's a behavioral question and it's asking, how did you resolve conflict on your team? In the situation, you can say the project I was working on, and this is what I was doing. So I was working on a website and I was implementing a form. And then when you go to the task, it's not my task was to implement a form. It's there was a disagreement with my coworker and my goal was to get the design approved. So it's kind of tricky when you separate situation and task. It's not actually your coding task, it's your interpersonal task. So when you get to the task, what were you asked to do? What goal were you trying to reach? What were you trying to accomplish? It's usually not a specific coding thing. It's more that, trying to convince the team or resolving a conflict. Next is the action. What approach did you take? How did you reach the goal, or what action did you take? And then the result. What was the outcome? Often talking about what you learned is also really helpful. So, you have a disagreement with a coworker. They say, I don't want you to implement this web form with this framework. I want you to use the other one. Whether or not you won the argument, you can still say, we ultimately went with their decision, but I learned quite a bit from it and I was able to, et cetera, et cetera. So situation, you can describe your entire project, the design that you were doing, and then the task is usually interpersonal, what action you took and what the result was. And the result doesn't always have to be, I won. It can be a negative result, negative, with a learning. So I'm going to give an example answer from my career. So tell me about a time when you disagreed with a proposal or approach on your team. When it comes to these questions, it's very negotiable. So I'm going to see this question and say, how about a time when somebody disagreed with me rather than me disagreeing with them? And you're like, it's 6 dozen or half dozen. 6 of one, half dozen of the other. Is it really important? Which one? So you can also discuss with them, would you consider an example of this instead? Or I haven't been in that situation, but I've been in this one. So that's okay to negotiate. So I can say I was on a project where I was building a mobile analytics pipeline, and I proposed an event-driven architecture with buffering, trying to avoid direct REST API calls. And so that's not my task. That's just the situation. My coworkers disagreed with my asynchronous approach. They wanted me to do synchronous calls instead. And so that's still the situation. And then the task is, I needed to get agreement on my team. We needed to make sure everyone approved the design. So just to be clear on that one, me designing a data pipeline was not the task. The task was getting approval and buy-in from everyone else on my team. So in this specific example, I would probably go into more detail and say, when it came to discussion, my coworkers described that REST APIs were more familiar with them because they were a mobile team and they weren't familiar with asynchronous programming or asynchronous event-driven design. So I was able to educate them on that pattern. They realized that it does have scaling benefits and it has benefits towards fault tolerance if servers are down. And they agreed with my approach, and we started applying that in other places. So the discussion here now, I'm kind of going through this one quickly, but you want to say, you know, what action did I take? I spoke to my coworkers, I educated them, and then as a result of this, my design was approved, the team learned as a group, and my coworkers went ahead to try to spread this design with other people. So you're like, great, I answered this question, but this will send a lot of signals. So some of the signals are, when confronted with a disagreement, I seek to understand and educate rather than combat. You were able to show empathy to people rather than saying, and I just threw a textbook at them to prove that they were wrong. So different things that you can try to approach of what human traits, what collaboration traits do you want to show here? Because I could have, you know, answered it differently. Like when they realized that I was smarter than them, they picked my answer, and that's how we resolved it. So you want to be careful about that, and really think about, you know, the company values, because some companies, they'll list humility and empathy. Some company values, like I like Amazon's, one of their company values is "are right a lot." And that means that you're right a lot. So you might want to highlight that you were right. Kind of an unusual situation. There are many questions. You can find tons of questions online. We're not going to go through all of these, but what we are going to do is we're going to go through a breakout session. So now that we are done with the breakout rooms, I'm going to move on to the next topic, which is graph data structures and algorithms, an ode to an ode. And if you like making punny titles to presentations, we are looking for presenters. It is one of the perks. So we're going to talk about what graphs are. And you might think, and this is where I'm doing something kind of interesting here. Sorry, I have a pen. And I'm drawing on my laptop screen with my pen, but yellow is not a great color. So you've got graphs like this. So that is not what we're talking about. Graphs are a relational data structure, and we'll be talking a little bit about how those work. There are two main components to graphs. So there's nodes or vertices, and we usually draw them like this, like a circle. They can have data. So you have a node or a vertex. I've almost always heard node talked about in sort of day-to-day computer science, and I've only heard vertices talked about more in the computational theory and math theory classes that I was in. So we have nodes, they can have data. And then we have edges, and they are lines. So you're going to have just a regular edge look like that. I'm actually artistic enough to draw these. But you might also have edges. Oh, that's a bit too curved. They don't have to be straight, but you might have edges, and they might have data as well. So your edges can have data, your nodes can have data. Your edges may also look like this, and we'll talk about what that looks like in the next slide. Oh, yeah, we just one day I want to finish this arrow here. Okay, sorry. I've got about 3 mice on my desk right now. Okay, so we got nodes and edges, and we need to put them together. And that's what graphs are all about. They represent relationships. So I will have a node A, and it has a relationship to a node B. So you've got 2 nodes and an edge. There are different ways that these relationships can work. So there's undirected and directed. So if I add a node C here, A, B, and C are related, but they're related by undirected edges. And I'll show you what directed looks like. So now we put some, oh, that's a terrible arrow. We put some arrows on here, and now it's a directed set of relationships. So when you have arrows, it means that when you start from A, so we're here in the undirected version. You can go to C or you can go to B. There's no limitations. In an undirected graph, everything can go two-way. But if you're at A in the directed graph, it's like there's one-way streets. You can't go to C, but you can go to B. And so that's the difference between directed and undirected. So usually when you talk about directed and undirected, you'll be talking about the edges or the entire graph. So you can say directed graph, undirected graph, or a directed edge or undirected edge. And so just to isolate it, the undirected edges are just going to be a regular line. The directed edge way, the other way, or bidirectional. Sorry, Google's telling me my mic is off. Okay, one thing to note, if we erase all of this, if I have my graph and I have A goes to C, goes to B, and I have this edge here, this one, that is an undirected edge in a directed graph. That is not valid. So if you have one directed edge, all your edges have to be directed. So in order to correct this, to turn an undirected edge into a directed edge in a graph, you just make it two-way, or you make it bidirectional. So that's a requirement on graphs. So we just talked about relationships. So let's talk about how you describe them. So we use the term neighbor. So a neighbor is the neighbor of a node is connected. It's a neighbor of node N has an edge to M. Okay, let's use the diagram. So if we look at B, B is connected to C by this edge here. So C is a neighbor of B because they're connected. Similarly, A is a neighbor of B. So B's neighbors are A and C. And because this is an undirected graph, you don't have to worry about the direction. When you get to directed graphs, it's slightly different, but we'll go into that in another slide. So this graph I'll be using to reference often. I'll try to bring it up as much as possible. But if you want to take a screenshot at some point and keep it handy, that works too. So that's how neighbors work. To see if we understand, let's answer some questions about neighbors in this graph. So you can take a couple of minutes, okay, not minutes, but I'll give you a few seconds to answer what are the neighbors of A and what are the neighbors of C. And then I'll circle them and see if I can bring up chat to see what answers we're getting. Actually, Becca can help me out with that. So Becca, let me know what's coming in.
So for neighbors of A, we're getting BDF.
Okay. And what do we have for C?
For C, BGE.
Okay, so I'm going to go over the answer. So A has 3 edges, and that is B, D, and F. So that is correct. B, D, F is correct. Good job, group. Next is C, and C has 3 edges as well, and they go to B, E, and G. So that is also correct. So that's pretty straightforward. We figured out nodes, edges, and neighbors, and that's really the biggest part about graphs, and then everything gets a little bit more complicated as you go on. Not too complicated though, it's all doable. So now the part is, you've got your graph drawn, and if you're in a job interview, you don't necessarily have a stylus and a touchscreen like what I'm using right now. And so you're like, well, how do we put this into code? And certainly you can't just shove a diagram into code. And that's actually what's nice about whiteboarding questions, that you kind of do that. But how do we give this thing to code? There are 2 strategies. And the first one I'm going to go over is called adjacency list. So in the top right here, I have this non-language specific pseudocode Python/Java representation of how you would create an object with an adjacency list. So you'll create a node class and it will have data, which is a string or a character in this case. And then it's going to create a list of the nodes it's connected to. And so that's how we get from neighbors to a representation. So you have the node value and a list of its neighbors. So like what we did on the previous slide, A has BDF, B has AC, and C has B and G. And once you fill this out, you've got the total adjacency list for the graph. So if you were getting the neighbors listed for the other nodes, I'm just going to add them in here. And you can follow along or correct me if I get anything incorrect doing things live. You always end up with a variety every time you try. F is A, D, and E, and G has just one neighbor. Okay, so that's all sorted out. Kind of makes sense, hopefully. But what if it's directed? So how do we represent a directed graph in terms of an adjacency list? And just like when I talked before about whether or not you can reach a node, so the difference here is it's the same graph, I've just added some arrows. So A can no longer get to B. So this isn't possible. And when we talk about get to, it's how we talk about graph traversal. So graph traversal is really what we go for. And each edge is like a street between two cities or two nodes. And you can only go down a street in the right direction. So you can't get to B from A. And that's going to impact its adjacency list. So we'll switch over to filling in that one, which might not be, it won't be the same as before. Oh, and one thing I wanted to point out that I missed here, if you look at the adjacency list of this graph, or of this graph, just going to change pen color to, I don't know, green. So if A has B in its adjacency list, B has A in its adjacency list. And that's because this is an undirected graph. This is a type of symmetry. So this will come up in our next representation, but when it comes to undirected graphs, this is an important feature in some cases. So you can, the relationship is symmetrical and that shows up in your representation. With the directed one, it's no longer symmetrical. So if we look at A and we try to construct the adjacency list, it's where can I get to from A? Does anyone want to take a stab at what A's new adjacency list is?
I'm seeing DF.
Okay, that is correct. So it is DF. And does anyone want to take a stab at B?
Just A?
Yeah, okay. So you can see that I'm going to fill in the rest of this and feel free to follow along in your head. See, I'll be slower than you. So you can see if I'm correct. D has no friends at all. It's very sad. F goes to D and E. And then G has no neighbors. And so that's very different. So if I go back to this one, everything had something. It was connected to something and it was sort of more of a full list. And I switch it over to being directed and suddenly it's a little more sparse. And you see that symmetry is no longer there. If there is a node in A's list, D, there's no guarantee that A is in D's list unless it has that bidirectional intentionally. So those are adjacency lists. Does anyone have any questions about those in chat before we move on to the next and slightly less straightforward way to represent graphs?
So this is like a good rule of thumb is like if it's a unidirectional edge, you know that since A is in B's list, B can't be in A's list.
It could be. So if I update this and I add a reciprocal arrow, this will change the adjacency list for A to include B. So now I've made that edge bidirectional, and so
Yeah.
it could be. But if you have a,
But if it's unidirectional, it could
Yeah.
be.
okay, sorry, I forgot, sorry, I might have skipped over that because I remember now that you said that. But yes, that is right. If it is one way, then they cannot be in each other's adjacency lists.
Okay, cool.
Okay, so now we have this one small table. Now we have this giant table. It's actually called a matrix. And if you took algebra or set theory, that's where all these words come from. So some of them are a little more mathy. So that's where the vocabulary, otherwise we could say adjacency table, not adjacency matrix. Okay, so how does this work? We have a row for each node and a column for each node. And I'm going to put -1s where it's the same, the row and column are the same, so that's for its own node. And the way this works is I'm going to go across and try to tell if there is a node between the column and the row. So if I'm starting on the left-hand side here with A, and I go to the second column, B, is there an edge between A and B? So I'm going to look at my graph. I'm going to see there is. So I'll put a 1 here to mean that there is an edge. Next, I go to C. Is there an edge between A and C? There is not. So I'm going to put a 0. And then you go through the entire graph and you try to fill it in so that it's just 1s and 0s, and then -1s for where it's, or nulls, depending on your language, where it's the same one. So, you know, A could be connected to A. You know, you could put it as 1 if you wanted to. There's different, you know, depending on your implementation. But this is another way to represent graphs, and it can come up from time to time, which is why it's worth going over. So to complete the row of A, for this A and D, what is the value that I should put in that square?
I see 1.
All right, that is correct. There is an edge between A and D. And for E?
0.
Yeah, we got a 0. F is going to finish the row of A.
1.
Okay, that is good. And finally, G.
0.
All right. So that is how we represent A's neighbors. And then we're going to go through and try to fill in the rest of this. So B is connected to C, is not connected to D or E. Actually, it's only connected to A and C. So I'm going to show you. So here, let me not skip ahead. So B is connected to A. And what we're going to see if I start filling these out is that there is symmetry again. So if you go along the axis of the -1s and you flip the table, the numbers are the same. So if I go along this flipped, and it's very hard to draw even with this capability, it's going to be a mirror. And that's because they're bidirectional. So if I only fill in the top half of this, the top half up there, it's actually going to tell me enough information because I don't really need to look at the second half because it's undirected and symmetrical. Let's see if I'm able to actually finish this. D to E, 0, 1. And so I'm not going to copy them over again. Too much thinking here. F to D is 0. But it will be the same. Actually, does anyone want me to fill in the full thing? Because I can do that if that would help. Okay, because we're going to move on to directed. And this time we will have to fill in the whole thing because it is not symmetrical. So I'm just going to fill this in with -1s in preparation. And we will, let's see, I'm going to fill in, let's start with B. So actually, let me fill in A first because it's a little bit more interesting when you're directed. So you have to choose whether you're doing the column is the source or the row is the source, because now you have to choose. So we're going to say that you start from the column, sorry, start from the row, and then this is the end. So if we start at A and we go to B, is there an edge from A to B? And that's going to be false. So you could actually have Booleans as well, but usually it's numbers. So that's false. So there's no A to B. What about A to C? You know, that's also false. Ones we do have are D and F. So those are the directed edges. In terms of the no symmetry, if we go from B to A, so that's correct. C to A is no edge, no edges there. So that first row, if you flipped it, it's no longer the same. So going back to this one, E, that's 0 and 0. So at the top row here, it's 1 0 1 0 1 0, and then if you go down the A column, it's 1 0 1 0 1 0. So that symmetry is there. But here, the top row is 0 0 1 0 1 0, and the first column is just 1 0 0 0 0. So they're no longer symmetrical. And again, it's an interesting trait because if you are, sorry, I'm trying to remove the, there we go. So if you are using an adjacency matrix and it is undirected, you only have to worry about that first half. You don't actually have to traverse the whole thing. So let's try to go through a couple of these after I've given examples. So from B to C, is that a 0 or a 1?
I see 0. And there was also a question, can you choose which is the start and which is the end, or is it always the same?
You can choose when you have a matrix, so it's like M and you have your two indexes, usually the start is the first index and the second is the end index. So you usually phrase it of, if you do M-I-J, I is the start and J is the destination. So in a sense, it is set. This is usually constructed as a two-dimensional array. And so the first index is the start and the second index is the destination, which kind of makes sense. I've represented it as a table, and you can decide in the table whether your column is the first or the row is. However you want to write it down, but it's kind of predetermined if you're using index notation. Okay, so for B to D, so we're at B and D, is it a 1 or a 0?
Zero.
Yeah, and actually doing the adjacency matrix for a directed graph is actually pretty boring, because you can either go through it like this, or you can look at B and you're like, it only has a one outgoing edge and it's to A. So you're like, okay, well that's all zeros. So you can do it the way where you go to the table and you check, or you can say, all right, I'm looking at C. It has two outgoing edges, one to B and one to G. I'm just gonna fill it in correctly there. Oh no, I dropped my pen on my keyboard. So it's only got, C only goes to B and G, and I can just fill in zeros for the rest because it's tiring to go through this entire thing. D, again, when we saw the adjacency matrix and I was like, D is super lonely. It has no friends. And same with G, I just fill it all in with zeros. And so I'm going to finish filling this in so that we can see how sparse this looks like in comparison to the other one, D and E, otherwise zeros. Sorry, you can definitely try this out at home as well. So this one, okay, maybe it's not this, but this one, there was a lot of ones, and it's fully mirrored. So there's almost twice as many ones. And here it's much more sparse. There's just a lot of zeros. So that tells us that the connectivity of the directed graph is lower than the connectivity of the undirected graph. When we talk about connectivity in graphs, it's how many neighbors. Like if you have high numbers of neighbors, then it's highly connected. And that's more into the graph theory. I'm not going to go into it today because there's a lot of graph theory. But going back to the representations, if you're in a job interview and they say, please, here's a graph question. How are you going to represent the graph? You might also be asked, what are two different representations of graphs? That has come up. And so you'll want to potentially answer, adjacency list versus adjacency matrix and which is better. When you think about the adjacency list, it is much more dynamic. You can just add nodes as neighbors, whether it's directed or undirected. The nodes don't all have to be stored in the same location. You could have nodes on different servers. So one node can point to a node on a different server. It does take up more space though, because in the case of the undirected graph, you duplicated all the relationships in their adjacency lists. And if you're in a fully connected graph, and a fully connected graph is one in which all nodes are connected to each other. This is probably one of the weirdest ways to draw a fully connected graph. Every node is connected to every other node. You're going to have, every single node is going to have an adjacency list of 4. That's a lot of space. But your adjacency matrix is still going to be 5 by 5, no matter how connected it is. The other problem with the adjacency list is that lookup time takes a while. So if I'm at A and I want to say, are you connected to D? I have to go through the list and check every single node. Again, if it's highly connected, that's n-1 operations to look. So the adjacency matrix is much more compact. It's always going to be n by n, where n is the number of nodes. Lookup is really quick. You just have the 2 indexes and you can tell if there's a connection. The only problem is that to change the number of nodes, you're going to have to recreate the entire matrix. So it's pretty costly to add and remove. But it can all be stored very efficiently in a single spot. So it can be good for serialization. So if you wanted to send an entire graph in a payload, or you wanted to save it to a single file, an adjacency matrix could be super useful. Now, when you talk about coding problems, most often given the option, I will go with an adjacency list. But occasionally you'll be given a problem where it's like you have a video game and you're given a grid, and you can tell whether, you can pass through a grid box if there's a 0 or 1, and it's not quite an adjacency matrix, but you start getting into this thing where the graph is represented as a grid and you can do traversals. So sometimes that will come up. But more often than not, you're going to get adjacency lists, and you may be asked about adjacency matrices as matrices is actually the plural as a follow-up question. So those are good to know. Any questions about graph representation? Okay. So we have graphs. Why do we want to use them? There's a few different uses that you can sort of come up with. People can sort of bring up. One of them is representing physical adjacency. So maybe I have a map, a flight path. So maybe Delta Airlines has a set of flights that they can offer, and they want to represent that as a graph. So you can go Seattle to Portland, San Francisco, where else? Vancouver. So we have Vancouver. Okay, we have these different cities. And then in addition, I did mention before that edges can have values as well. So we're actually going to put costs on here. So now we use a graph to represent not just flight paths, but costs. we can add on to this even more to say that there's only a flight from Seattle to Portland, but not from Portland to Seattle. And so we can add edges here to say, these are the flights available. This is what they cost. And so that's one of the common uses of graphs. And you'll see that in certain problems like the traveling salesman problem, which more graph theory that I will not go into today. Another use of graphs is trees. If you are familiar with trees, we did a previous talk and Daniela, one of our volunteers, presented that. So trees also have nodes and edges. And they're super useful. So trees are a subtype of graph. And one example of trees that is quite popular is trie or tree. I say trie because I want it to be clear that I'm not saying the word tree. But these are structures used for predictive search. So if you go to Google or Amazon and you type in a few letters and it tries to tell you, did you mean this? Or like autofill it in, that's what these are for. And so these will be structures of letters. I'm trying to come up with something. And so it will traverse these. Oh, sorry. Going too far. So it will traverse these and try to find predictions for the text that you entered. So that's a really nice use of graphs. And I'm not going to go into this because it will take a while, but you can solve Sudoku with a graph. And if you want to look it up, you can look up K-coloring as a graph problem, and that turns into 9-coloring, which is Sudoku. So that's kind of a fun one. You can solve puzzles and you can solve different sort of combination problems using graphs. It is not the most efficient way to solve Sudoku, but it's a way to solve Sudoku. And that's K-coloring is one of my favorite graph theory problems. And I think that says something about me that I have a favorite graph theory problem.
Hey, Alicia.
Mm-hmm.
That flight pattern thing, what is that called again?
So this is just, it's a graph, it's a directed graph with costs on the edges.
Oh, okay.
Yeah,
So
but if you did want to look up something, you can look up the traveling salesman problem. And that is a famous problem where it uses this type of graph where you have cities connected by roads. And the problem is like, can you get to all cities without visiting a city more than once? And so that's a special type of problem that people talk about a lot in terms of graphs. But if you think of, again, social media as well as another one where you can model relationships. But you know, when you're trying to find a flight path between, I mean, this graph is pretty terrible for flight paths because you can't really get from Portland to anywhere. But it's a way to express that. And similarly, you can use them in terms of language modeling. And so that's used in machine learning as well. So machine learning is trying to train models to describe relationships. And that's also an area where graphs come in. There's many uses for graphs, and they can be quite fun to work with.
Also, I had a thought come to me about the adjacency matrix, the directed one. So I guess I was wondering, when you have the bidirectional versus unidirectional edges, is there one that you would see is more common than the other?
As in whether you have directed graphs versus undirected graphs?
No, because undirected would be no arrows on
Okay,
it.
so you mean that in this relationship between A and F, you have two-way versus just one-way?
Yeah.
They're all equally common. I've made them all one-directed, which retrospectively, not the best example now that you bring it up, but there's no restriction. You could have all bidirectional except one. And because of that restriction, where if you have one directed, all of them have to be directed, and you have to translate to bidirectional, that restriction is still there. So there's no common versus uncommon. And when it comes to job interviews, it is more common to have undirected graphs than directed graphs, but there's a lot of implications there. So you want to ask, is this directed, is this undirected? If they give you a very explicit graph question, like here is a graph, traverse it, you'll want to ask.
Okay. And so when you say all but one, so like you can't have all of them be bidirectional because then it would just be the same thing as an undirected graph, pretty much.
Yes, but stating that, being like, by the way, if all your edges are directed and bidirectional, you actually have the equivalent of an undirected graph. That's good to point out. There are some people in discussion that are like, there's no such thing as an undirected graph. There are only graphs with bidirectional edges. This is like a semantic kind of discussion. But as you are thinking through, it's definitely a great thing to think through and just comment to your interviewer to show that you understand the differences.
Okay, thank you.
Yeah, no problem. Okay, so now we get into graph traversal. If you go back to the examples I had, which I'm not going to go back to them because it's not my best example of art, you want to traverse to say, I want to find the shortest flight path from Seattle to Philadelphia, or I would like to go through my predictive search tree to find any predictive completion for this word. Like spell check can also be thought of similarly. So I just wanted to find a first thing that people could mean. And so you have two different search algorithms, breadth first search and depth first search. And the main difference is that breadth first search will give you the shortest path and depth first search will give you any path. Could be the shortest, could be different. So before we even get into implementation or what they mean, breadth first, if you hear shortest or fastest or cheapest, breadth first. If you don't hear that restriction, you can go with depth first. And in that case, what you choose depends on your preference, but we can go over a couple of the differences. So breadth first is called breadth first because when you are traversing, and I'll go through a traversal, you first look at nodes that are closest to your starting point before looking at nodes further. So closest first. Depth first is furthest first and then closest. So with depth first, you're always trying to go deeper. And with breadth first, you just want to collect everything at the same level before you move on. So breadth first search is optimal but not faster in terms of how long it takes, time complexity. And depth first can be faster in very special cases, but it may not be optimal. So to spoil it for you, the time complexity for both of these is OVE. I'm pretty sure. I forgot to write it down, but it's the same for both because their worst case is identical. So if someone's like, what is the difference between time complexity of breadth first and depth first? It's a trick question. They're the same. I have been asked that question. Okay, so with breadth first search, what we want to remember is we want to go to the closest node before we go to the furthest node. And so when I'm going through traversal, like if you think of this as an adjacency list, I'm going to start for this graph, I will treat the top as first, and this will make sense in a second, and then bottom is last. Okay, so we're going to go through breadth first. We're going to start at A. And so when we are at A, we say our traversal path is A. So we start there. Now we have a list of potential neighbors. So we have B, D, and F. So we have our adjacency list that we built up. And I need to pick one of them to go to. And so I'm going to go with the visually what's on top first. So that's what I meant by this here. So I'm going to look at B first. So my next iteration is going to go to B. So I can say that the next step in my traversal path was B. So if I want to go to a closer node before going to a further node, which node am I going to go to first? Am I going to go to C, which I'm now aware of, or am I going to go to a different node? So I guess C, D, and F are nodes that I'm aware of that I haven't gone to yet. Becca, do we have anything in the?
I see F.
I would say C because it's the shortest path.
Or C or D/F. Yeah.
Okay, so we want to go to the nodes. So we have our start. We want to go to nodes that are closest to the start before going to nodes that are furthest from the start. So C, so these are all one step from the start. If I go to C, that's actually 2 steps from the start, but we still have 2 nodes that are 1 step from the start. We want to go to those 1-step nodes before we go to the 2-step nodes. So our next candidates are D and F. So we're going to go to the visually top first. So it's going to be D in this case. So we are aware of D and we're aware of F. So we're going to go to D. So now so I'm marking these that we are aware of C and we are aware of F. So if we're going to go to the next closest, so we want to stay as close to A as possible, are we going to look at F or C next?
Okay, so now it'll be F.
Yeah. Sorry, it is, I haven't gotten the best method of concisely and clearly describing these. It's really easy when you're going through the diagram.
I got confused because you wrote at the top A, then B. So I'm like, okay, we're at B now. So what's closest to B? We already saw A.
Yeah, so maybe I would say, maybe I should change this to like touch order. So touch, I use that because that's the command in Linux where you tap a file. So it's like maybe tap order. So the ones that we sort of examine more closely. So we start by examining A, then B, then D, and then F. So that's right, because we want to make sure, change color again. We want to get to this first layer. We want to talk to all the one-away neighbors of A before we do any other nodes. So for the next iteration, after we've gone to F, switch back to green so I don't confuse everyone. So once we get to F, we've now looked at all nodes except C and E. At this point, C and E are kind of the same distance away, but we're going to go top first. So there's no wrong answer with C and E, but just based on my definition here, we're going to go at C next. So we've hit C, and now we are aware of E and G. Which one are we going to go to next?
E.
Yeah, so we got E. Now we got to E, and then the last one we have that's far away is G. So I'm just going to annotate the edges here. So that's 2 away, and this is 3 away. And I'm going to get more colors out. I'm trying to avoid anything that might, okay. So everything in this purple box, this first box that's reverse L-shaped, this is 1 step away. And we looked at all of those first. So in this first block, we looked at all the ones that were 1 step away first. Then our second block was 2 steps away. And we looked at all of those before getting to G, which is the only one that's 3 steps away. 1, 2, 3. So does it make sense that we looked at the closer nodes before we went to the further nodes?
Yeah.
So I'm going to erase all of this.
You know what might help? Just like for future reference, like if you went and just turned it on its side, the graph itself, so like the A and F is on the top, because then, I don't know, it just seems like to me that visually it'd be a little less confusing when you're going top down.
Okay, thank you for the suggestion. I'm just going to, again, label these. So we start at A, we look at B next, then D, then F. I'm just wanting to make this a little bit cleaner to reiterate that. And definitely, if you're in an interview, sometimes you'll be given graphs that look nice, sometimes you won't. And sometimes you'll be given an adjacency matrix and it won't be as fun. So that's BFS, and we're going to implement that in a second. But before that, we'll go into DFS. And spoilers, I'm going to be implementing them iteratively. But DFS is really great if you want to implement it recursively. So as a try-at-home problem, try to implement DFS recursively. That means when you write a function and call itself. But I will be doing it iteratively because there's a fun trick between the two, DFS and BFS. So we're back at DFS traversal here. We're going to start at A. And when we're at A, we know about B, D, and F. So we're going to call this the tap path. So what do we tap first? So we're at A. We want to pick things that are as far away as possible. And since we're going to do the same thing where we're going to chop first, we're going to start with B. This is going to be our second destination. We're at B. And now we have C, which is 2 steps away from A, D and F, which are both 1 step away from A. So when we're going through DFS, we want to go deeper first. So which node is going to be the furthest node to go to next of C, D, and F?
Now it's C.
Okay, that is correct. So we've got C. And when we're traversing, the first time we see the node is, so we measure the distance by the first time we see the node. So we could have gotten to E by going through F, but instead we've started at C. So it's all about sort of what do you see at that time. So when you're running code and you're at C, you know about C's adjacency list. You do not know about F's. So you go to the nodes in the order that you traversed their predecessor. So we're at C. We know about D, F, E, and G. We're going to, what would the next node we look at be between F, E, and G?
See G?
Right. So technically, E would have been fine, but because we're doing top to bottom, that's right, it is G. So now we have no more to go to. So we go from G and we kind of bounce back to C. So now we're at C and we know about E and F. Which will we go to?
E?
Yes, we're going to go to E. And this is where things get kind of interesting. So we haven't been to F yet, but we know about F and D. So along one path, so we're currently sitting at E in terms of our execution context. We're at E. And our options are going to D from A, F from A, or F from E. So we're actually going to go to F, but the path we took is going to be A, B, C, E, F, not AF. So I'm going to just answer this one that the 6th step of our path is going to be F. So the last node D, the same thing's going to happen. We're going to hit D 7th. And so we've actually traversed almost the entire graph in a single path. So you're going to get an output that's A, B, C, E, F, D. That is an answer to give me a path from A to D. So if we were asking the BFS question, what is the path between A and D? BFS would have given you AD. because it looked at D third and it found it. But if you look at DFS and you say, what is a path between A and D? When we traversed it, we went from A to B to C to E to F, and then we finally find D. So our path is size 7, whereas in BFS, our path was size 1. So that's where you can have that difference. Now, when it comes to graph traversal, sometimes you're not being asked to find a path. Sometimes you're asked a different question, like, can you get to all nodes from A? And if you're in a directed graph, then sometimes you can't. So that's sort of a different, that's sort of the difference between BFS and DFS. So can you get to D? If you do BFS on this graph, it's a path of length 1. If you do DFS on this graph, it's a path of length 7, which is crazy different. And I'm gonna go and switch over and implement it. And I'm gonna stop the Google Hangouts call I have with myself. Stop share, and then I'm going to go over to IntelliJ. And I'm using IntelliJ, which is a free Java development, integrated development environment. I will be using Kotlin. It should still be pretty understandable, hopefully. So I have this image of the graph we're working with up, and I'm going to first create the graph in code using not adjacency matrix. I don't want to use it. I don't like those. We're going to use an adjacency list model, and then I'm going to traverse it, and we're going to see what order we get that traversed in. So the first thing is, how do we represent our graph? So we're going to have, the quickest one is BFS. So BFS, if you're asked shortest path, BFS will give you the shortest path. If you're asked for any path, like, you can think of it as kind of, if someone's on like an Easter egg hunt, you have multiple strategies where one person sort of goes in a spiral and looks for Easter eggs within a particular region, and another person or child just goes way out into the furthest possible location to see if they can find Easter eggs. And you're like, those are two different strategies. The only difference is that the person who goes further is going to find the furthest eggs, and the person who's nearer is going to find the nearest eggs. When it comes to actual time, the person who's nearer might actually find more eggs because of the closeness. But anyway, so you can think of it as like, I think of it as two kids, where one is just going way out there and another one kind of stays close to home. Okay, so we have this representation where, again, we have the node. It has data, which I'm using as a string, and it has neighbors. And I do apologize because sometimes I spell neighbors with Canadian spelling and sometimes I spell it with American spelling. It's something I don't realize I do. I'm Canadian, which is why I have a poppy today, because it's Remembrance Day, and happy Veterans Day. I say happy, but happy Veterans Day to everyone, and Remembrance Day if that's the holiday you celebrate. So we have our data and our neighbors. It's pretty straightforward. You've got a letter and you've got a list of letters. Well, you've got a list of nodes, and it's okay for it to reference itself. So now I have my test, and in my test, of course, we like unit tests. I like unit tests. I have my, BFS gives shortest path and DFS gets a path. And in the test cases, you can see that one path is longer than the other. We'll talk about that. But when I want to construct this graph, so I'm first going to create all my nodes. So A, B, C, D, E, F, and G. I've created my nodes. And then I'm going to add those relationships. So for A, my neighbors in that adjacency list are B, D, and F. For B, I add A and C, etc. And so that's exactly the same as the adjacency list that we built earlier on. So now, fingers crossed, that's a graph. Is not easy. Like, you can't do like a print statement. This is my graph. It's kind of hard. No matter how you print it, it's going to look a little weird. And so that's why I have this two-string method I've overridden. This doesn't look great, but it will look like this, where you have a node and a colon, and then it's going to give you the list of its neighbors. So I've chosen to override a print statement. So this is like kind of sane and readable. So how do we implement this? So when we are asked the graph search problem, we're given a node. So this is your graph. And that's kind of the fun thing about the adjacency list is you have a one node and you're like, this is the entire thing. And you can actually get to all the other nodes because you have the adjacency lists, assuming that it's a connected graph. If you have a disjoint or disconnected graph, that's a separate problem and we're not going to worry about that. Worth asking in an interview, but it's an uncommon situation. So what's interesting about this, and that I have sort of caught people out when I've interviewed them with graph questions. Yes, I'm the terrible interviewer that asks graph questions. You want to return a path. I'm not asking you to traverse. I'm not asking you to give me a true false. Is there a path? I want you to return the path for me. And that's going to make it a little bit more complicated. And I will go over that in a sec. So what we want to do is we're going to have a current node. So we're going to be traversing and we're going to say where we are. We're going to say while, that's not how we're going to do it. Sorry, I'm trying to remember my flow here. So when I was going through the traversal, I sort of had a list of candidates. So we're going to keep that list of candidates. We're going to say candidates. And I'm going to make this a queue. And the reason I'm going to make this a queue will make a little bit more sense once I get the implementation going. And one thing that I learned is that you can't just have, there's no queue, there's no native, or it's not native, there's no actual implementation of queue in Kotlin. It wants me to have a mutable list, I think. Nope. Let me check my notes here. Oh, that's right. Okay. This actually tripped me up a little bit more. If people know Kotlin, this is me and my Kotlin stuff. Okay, so I have a list of candidates. It's going to be a queue. If you remember stacks and queues from last time, we're going to put an item to the back of the queue and we're going to pop an item from the top. So these are our candidates. Our candidates are going to start off with the first node. So we're going to have the start node. So that's where we're going to start. We're going to keep going. Is empty. Well, we still have candidates. We're going to do what? We're going to determine which other candidates we should be looking at. So if I'm at a node, if I'm at A, current equals candidates dot remove. So I go to my queue, I take the first one off, I might be at A, and I want to add B, D, and F to my queue. So I look at them later. So I say for current dot neighbors for each. So for each neighbor, I'm not super happy with autocomplete on this. I'm going to add it to my queue. I'm going to take my neighbor and I'm going to add that. So now my queue is growing. So every time I'm at a node, I collect my neighbors and say, please look at these later. And you're putting all of them at the end of the queue. So the first ones that get put in the queue are the ones that are closest. So once we've done that, we're now going through our graph, and we remove the top of the queue and we add neighbors, and we remove the top and we add neighbors. But unfortunately, this is going to go forever because we're just going to keep adding neighbors and neighbors and neighbors, and it's never going to end. So how do we make sure that our code stops? And so when I was drawing this out, I had these little dots that I was putting on the nodes. And so we kind of have to say, we've already looked at this one before. Don't look at it again. So the way we're going to do that is we're going to keep a list of visited nodes. And I'm going to make that, I'm going to make this a mutable set. Doesn't really matter. Use your, I mean, I say mutable set because sets, you can do hashes on them and it's quick lookup, but to prefer sets if it's a hash set, but that's kind of getting into implementation of the language. So I won't get too far into that. There we go. So every time I get a node, I want to say I've already visited this one. Don't look at it again. And so depending on how you want to implement this, I'm going to say that before I add my node to a list of nodes, like my to-do list, my queue is my to-do list. Before I add it to my to-do list, I'm going to say I've already looked at it. So I'll say visited.add start. So I'm going to say I've already looked at this. I've put it in my queue. And now I go and do the same thing with neighbors. So I'm going to add a neighbor. I'm also going to say I visited it. Okay, cool. So I go to my node. I check its neighbors. I say, all right, I've already looked at all of these. I'm just going to put them in my visited list. But how do we actually do the filtering? So we have to say, well, what do we want to do if it's already been looked at? We probably don't want to add it to our to-do list because we already did it. So we will say if neighbor in visited. So if I already looked at it, okay, this is something I think is funny about Kotlin is I can just do not on the in. Something that I find fun. So if we haven't looked at it yet, put it in my queue and say that I've now visited it. So this means that I'm not going to end up reloading the neighbors multiple times. So that prevents an infinite loop, which is good. We don't like infinite loops. If you have implemented BFS and you get an infinite loop, you might not have put things in the visited list. Okay, so we have our queue of to do. So we add current, we add its neighbors, and because we added the neighbors first, they're going to be earlier on in the queue. So as we go through like the different layers of the graph, the further items are going to be at the end of the queue. And because we're using it as a queue, the oldest gets popped out first. So that's FIFO, first in, first out. So that's what makes this closest first. Now, if we go to DFS, it's actually going to be the opposite, but we'll get to that with DFS. So here we go through each neighbor. We're not actually doing anything with it right now because our goal was to find the target. So our target is a string. So we say, all right, so we have our candidates. We're popping from the candidate list. There's two options here. One, you can say if the current dot data is equal to target. So you can do that here. So every time I examine a node, I'm going to say, okay, are you what I was looking for? And then I do whatever I do. You can also check for it in this for each neighbors. So it's up to you. You could save like a couple of iterations that way so that you don't actually look at all the neighbors. For simplicity, I'm just going to put this here, but you can do it either way. So if my data is the target, I found it. So I return what? What do I return? I'm supposed to return the list of all the nodes, the path. So if I'm in this graph and I want to say, I want to go from A to G, I need to go A, B, C, G. I need to somehow track that. So how am I supposed to do that when I just went and found all the nodes? Like, how am I supposed to remember? There are different ways to do it. And my way of doing it, which is, I don't want to call it lazy, but I think that it's less computational effort, is I'll go back to my data structure that's a node, and I'm just going to add source. And this isn't great because it doesn't necessarily represent graphs. Like a node can have multiple sources, but I'll add the source as a tag to say, when I was traversing, where did I come from to get here? And that's going to help me go backwards in my path. So I can do we could do a method here. I'm actually just going to I'm going to copy this because we are getting close to the end of time. So this is a method where I give it a node, and again, we take the current node as the start, and I keep going backwards. So I add the current node to the path, and I advance backwards, current equals current.source. And I keep going while there's still a source. And that's going to give me a list of like G, C, B, A. So I'm going backwards from the node I found. And then I reverse it to get the path. And so this is fine. You can also keep context. It's a little tricky because you're going back and forth in traversal. It can be a little easier when you do DFS recursively to just go back up your call stack. So that's something that's nice about DFS recursive that you can try out. So then I'm going to do get path from node current, which is great, except I haven't been tracking the path. So now I have to add that in. So I will do neighbor.source equals current. So that's me changing it, and I need to make this bar instead of val. So that's me saying, okay, this is where I came from. And then when I found the data I want, I just traverse backwards on the source and then reverse the list, which is one way to do it. Again, I consider it a little bit lazy because I don't want to do the additional computational effort. So that is BFS. If I go to my graph search test, I take my graph example here and I try to find G, and I expect it to have a certain path. I don't know if it's actually going to have that path because, I made a mistake. I have to put a default value, otherwise it gets upset with me.
Alicia, there's a question. Can we collect each node value as dequeue each node and return that collection?
So the reason why, now let me see if I can pull up that question. The reason why we can't do the dequeue is because when we were going through traversal, it'll be like, I go to A, and then I go to B, and then I go to D, and then I go to F. And that's the order in which I am looking. And then I'll go to C, and then E, and then G. That's not actually the path we're looking for. That's the traversal order. So they're not the same. In DFS, it is though. So in some cases, you have to be careful about DFS there. But the order in which we traverse the candidate queue is not actually the path. And that's what makes this tricky. What do you want here? Yes, it could be private. Thank you, IntelliJ, for telling me how to write my code. Failed Stack Overflow. Oh, good. We're gonna, I do apologize for this, but I'm just gonna copy paste my old invitation. I do have this on GitHub as well. I can just do a revert. It's approximately the same. So I have a next queue. We add start and visited like before. I'm gonna run this, not in visited, it's current. Okay, not really sure what my Stack Overflow was, but it's almost certainly, you know what I think it was? I think I put next is empty instead of not empty. Gotta worry about that. Okay, so I'm going to pull this up here. I realize this is like obnoxious. So in the method that I have here, I am printing the current. So every time I examine a node, I print it. So in this lower view here, I first went to A, and then I went to B, and then I went to D. So this is the order in which I'm looking at the nodes. And that's exactly what we did for the breadth first traversal. Then we go to F, and then C, and then E, and then G. And I finally get to the found print line here when I get to G. When I go to the test, my path is not the same as the traversal order. My path here is A, B, C, and G. So this is the path that I output, but this here, the print output system out is the order in which I traversed. And so that's where the DQ order is different than the order that you found when you were traversing. So what I'm going to do is quickly go over DFS. So I do apologize. That's going to be kind of sudden, but it's actually pretty fun. So I can actually just copy this and paste it. So we've got BFS code here. And the only thing you need to do to make it DFS is to change your queue into a stack. The end. That is now DFS, which I think is pretty cool. All right, we got to do some API changes. And that's it. And that's why I like doing them iteratively, because all you got to do is remember one implementation, and it's going to be the exact same one for BFS and DFS. Let's do a push. I have to change the API for that to make sure it goes. And so it's for BFS, it's FIFO, first in, first out. The first one I saw is the first one I look at. For stacks, it's LIFO. For DFS, last in, first out. The last one I saw, which was pretty far away, that's what I'm going to look at. So I go to my graph search test, and the path is different. So we start off at A, and it's actually going to be a little bit reversed. So if you think about the way we're traversing it, we look at A, we've added B, D, and F to our stack. And so F is at the top, which is why instead of the walkthrough that we did, where we did top to bottom, it's actually going to be bottom first. So the path we end up with is A, F, E, C, G. When we go through A, F, E, C, G. So that's the BFS path, or the DFS path. Let me see if I can actually run this, and then we can look at the traversal order in the output. Now, this one's interesting because we basically went directly to G. So we went A, F, E, C, G. That is exactly the path we went. So we just kept going until we found G. In this case, we didn't have to do any backtracking. So the path was equal. But if we were looking for, say, B, we would have gone A, F, E, C, G, and then B, or something similar. So the cool thing is, again, the only difference between BFS and DFS is whether you're using a stack or a queue. Stack is for DFS and queue is for BFS. We're pretty close to time. So hopefully I covered most things about the basics of graphs and graph traversal. There's a lot more stuff that's really cool to learn about graphs. Before we end, are there any questions? Oh, I do have my code on GitHub somewhere that I can share. I can share on the meetup. And I will actually stop recording now.